Hi guys, this is Dr. Manjunath Chennapgod from Anveshana Academy, Bangalore, India. Dear students, in the previous video we discussed about Carnot Cycle, assumptions made by Carnot Cycle, what are the key points for Carnot Cycle we discussed in detail. Okay, now I will move towards next topic, Carnot cycle working. Okay, dear students, once again I will refresh the Carnot important four processes and I will try to explain you how the Carnot engine works. The first process, as I told in the previous class, there are four important processes. Two are isothermal processes, two are adiabatic process. Okay, the first one you can see, dear students, here, adiabatic as well as isothermal process. The first one you can see, dear students, here it is a isothermal expansion process. Here what will happens, what I told, the heat is added at constant temperature. That process we can call it as a isothermal expansion. Dear students, as I told, assume that it is a adiabatic wall AW and it is a diathermic wall DW. When we are going to attach this wall with the heat source to the piston, so heat is going to supply to the gas, hence the piston is going to expand. If the piston start to expand due to supply of heat at constant temperature, that process we can call it as an isothermal expansion process. One thing. Second one, adiabatic expansion. Dear students, you once it is expanded, heat is added at a constant temperature, that we call it as isothermal expansion. Immediately what I will do, I will remove this diathermic wall and I will put an adiabatic wall. Hence what happens, the whole piston become insulated, but because of the heat which is present in the gas, it cause explosive force over the surface of the piston. Still the piston is start to move and it is moving or expanding. That process we can call it as adiabatic expansion. When you are going to cover complete piston with the insulated wall, heat is there inside, but heat is not at all transferring outside. Because of that heat, the gas is going to create an explosive force over the surface of the piston, hence the piston is moving. That we can call as the expansion, but there is no heat transfer from system to the surrounding. That we can call as a adiabatic expansion. So that is what adiabatic expansion. What is adiabatic expansion? The fluid is going to expand the piston, whereas heat is not at all transferring. That is what second adiabatic expansion. Okay, fine. Third one, isothermal compression. Once the expansion work is done, we are going to compress the gas. When you are going to compress the gas, at that moment what I will do, I will remove the adiabatic wall, I will put a diathermic wall to the cylinder head. Then what happens, when you are going to compress, right, the heat is going to generate inside the cylinder, in the gas. That heat will be taken away from the cylinder to the outside with the help of a diathermic wall. That means what, heat is getting rejected at constant temperature. Again the temperature is at constant. That means what, heat is rejected from the cylinder, from the system to the surrounding with the help of diathermic wall at constant temperature. That during compression, that process we can call it some isothermal compression. During compression what happens, heat is generated, that heat is removed from the cylinder to the surrounding with the help of a diathermic wall. That process we can call, at a constant temperature, that process we call it as a isothermal expansion. Okay, the fluid is compressed where heat is rejected at a constant temperature, that is isothermal compression. Fine. Fourth one, adiabatic compression. Immediately what I will do, I will remove this diathermic wall, I will put adiabatic wall. Hence you are keep on compressing the gas, but you kept a adiabatic wall here also, then that means what, the piston becomes completely insulated. That means there is no provision to transfer heat from system to the surrounding, but still you are compressing. That process we can call it as a adiabatic compression process. Adiabatic compression process is nothing but what? The fluid is compressed without heat exchange or without heat transfer. Hence, that process we can call it as adiabatic compression. These are the four processes play a very important role in the Carnot engine. Okay, to explain the Carnot engine working principle, these four processes are very important. Okay, how it is that we will study here now. Now, dear students, what he has done, saw the Carnot. He has taken in a piston and cylinder arrangement, cylinder and piston arrangement. That cylinder, you can see at all sides, that cylinder is well insulated with a wall. That wall we can call it as a adiabatic wall. That adiabatic wall we can call, or we can call it the insulating wall. That means what? Heat is not at all transferring from system to the surrounding or surrounding to the system. But one end is free here now. The cylinder head we can see it is a free. Sometimes we will make this cylinder head as a insulation. Sometimes the cylinder head we are going to make it as a conduction. How it is that we can see here, dear students. Now what he has done, he considered two sources here now. One is heat source, which is working at a temperature T1. Second source is heat sinks, that is working at a temperature T2. Okay, so now one thing, two sources he has considered at different temperature T1 and T2. Okay, and he has considered two walls here. One is diathermic cover, another one is adiabatic cover. You can call cover A and cover B you can call. Okay, initially what he has done, dear students, he interacted this heat source to the cylinder with the help of a diathermic wall. He bring this heat sink and he attached to this diathermic wall. Then this diathermic wall is connected to the cylinder. Hence what happens, because already you know it is a heat source. Heat is going to transfer from heat source to the diathermic wall. Then diathermic wall allows heat to cylinder. Hence the heat is getting transferred from heat source to the cylinder. Then that amount of heat transferred to the cylinder is represented as a Q1, and that heat is getting transferred to the cylinder at a constant temperature. The temperature we can call it as a T1. The heat is supplied from heat source to the gas with the help of a diathermic wall. That too at a constant temperature. That constant temperature is represented as a T1. The amount of heat supplied is represented as a Q1, dear students. Okay, because of this heat supplied, then what happens, the gas is going to absorb the heat. Once the gas absorbs the heat, what happens, pressure and volume is going to increase. Once the pressure and volume increases, that means explosive force is going to exert over the surface of the piston. That piston we can see here, dear students. Okay, that gas, what it will do, it is going to create the explosive force over the surface of the piston. Hence the piston will start to move from this point to, you can mark, I will mark it here now, this point to this point. This we can call it as a point 2, dear students. Okay, this we can call it as a point 2. Okay, now piston is moving from 1 to 2, but what we are doing, continuously at constant temperature or supplying the heat. Because of that constant heat supply, the piston moved from point 1 to 2. That we can call it as a isothermal expansion. Isothermal expansion means what? From point 1 to 2, the piston is moving because of heat addition at a constant temperature. That process we can call it as a isothermal expansion. That you can write it here also. In the PV diagram, as I told, when we are going to supply heat, right, pressure is going to decrease, whereas volume is going to increase, because pressure is going to act over the surface of the piston. Hence the piston is getting expand. When it is going to expand, the volume is going to increase, where the pressure is going to decrease. That you can see it in the PV diagram. So pressure versus volume diagram. So initially assume that, dear students, piston is at particular point 1, that we can mark it as a point 1. So when we are going to supply heat to the piston, heat to the piston is moving from point 1 to 2. That means what? It is expanding, whereas volume increases, pressure decreases. That means what you can see here now, pressure is going to decrease, whereas volume is going to decrease when it reaches at the point 2. So what you did now, from point 1 to 2, what you done, you supplied a constant heat. That heat supplied is represented as a Q1. So at point 1 to 2, what you have done, with the help of diathermic wall and heat source, you supplied the heat. That heat supplied is represented as a Q1. At what temperature you have supplied the heat? At constant temperature. That constant temperature is represented as a T1. Hence, the temperature at point 1 and point 2 is remain same. That can be marked as T1 is equal to T2 is equal to TH, where TH represent higher temperature or source temperature we can call. Okay, this is what isothermal expansion. Dear students, what I will do now, isothermal expansion from point 1 to point 2, it's happened. Now immediately what he has did, he removed this diathermic wall, immediately kept the adiabatic wall to the cylinder head now. Then what happens now? Complete cylinder, piston and cylinder arrangement you can see, it completely it will become insulated or adiabatic wall. But there is no chance of heat transferring from system to the surrounding. But heat is there already inside the gas. That gas, what it is doing now, still it is putting pressure on the piston. The piston will already it is there here, right? Suddenly once you put the adiabatic wall, the gas having heat inside it, but still what will happen now? There is no provision to transfer heat. But that heat, hot gas, what it will do, it is going to create the explosive force over the surface of the piston again. Still the piston, what it will do, it will start to move to the point 3. Then we can call again the piston is still expanding. That expansion work we can see here now, dear students, when the piston is going to expand, right? So expand, right? That expansion work is represented by WE, the expansion. Okay, expansion work is represented as WE actually. Okay, fine. Still now, but there is no heat transfer at all outside. But what happened? Heat is inside, it is there. But still the piston is going to expand. That process we can call it as a adiabatic expansion. Expansion is taking place. Fine. But there is no heat transfer from system to the surrounding. If there is no heat transferring, but the piston is getting expand, that process we can call it as an adiabatic expansion. Hence, the piston moved from point 2 to 3, but there is no heat transfer at all. That process we can call it as an adiabatic expansion. Hence, the piston is moved from point 2 to 3, that is point 2 to 3, that we can call it as an adiabatic expansion. And where temperature you can see, where temperature T3 equal to T4, that is equal to TL, I will tell. Okay, now you are at particular point 3. Now I will start with point 3 now. Now work expansion is done. The piston moved from point 1 to 2, 2 to 3, expansion. You come reverse now. Okay, reverse from 3 point. You can call it the starting point 3. Then piston is now assume that you are going to compress. Just a minute. Okay, fine. Now initially your piston is at particular this point, right? This is what starting point now 3. Okay, so now what you do, you compress, you start to put a work pressure on the piston. Hence you are going to do work on the piston. That work done on piston is represented as a WC actually. Here it is a WE, you make it as a correction, WC, compression work. When we are going to put a pressure on the compressor, right, already gas inside it is there. Okay, and what I will do, I will remove this adiabatic wall. I will put a diathermic wall here, diathermic wall, and I will connect heat sink to cylinder with a diathermic wall. When we are going to compress the gas, right, heat is going to generate the inside the cylinder. That heat is rejected to the sink with the help of a diathermic wall at a constant temperature. That constant temperature is represented as a T2. The amount of heat rejected from system to the surrounding is represented as a Q2. The amount of heat is rejected from system to the surrounding is represented as a Q2. So when the piston moved from point 3 to, I will make it here, from 3 to 4. The piston is moving from 3 to 4. You are going to do compression. During compression, heat is generated. That heat is rejected to the heat sink at a constant temperature. That we can call it as a T2. The amount of heat transferred is Q2. That process we can call it as an isothermal compression. Isothermal compression. Heat is there. Some amount of heat is there. Okay, some amount of heat is there, but you are compressing. That process we can call it as a isothermal compression. 3 to 4 is isothermal compression. that you can see what actually happening during the isothermal compression. Heat is getting rejected. That rejection heat is represented as a Q2 at a constant temperature, that is T2. When you are compressing, right, you can see, the volume is decreasing here, whereas pressure is getting increased. It's a vice versa. In expansion, the volume increases, the pressure decreases. In compression, the volume decreases, pressure increases. Okay, so now, so what I will do, I will immediately remove this diathermic wall and I will put adiabatic wall. Once the piston reaches point 4, immediately what I will do, I will remove diathermic wall. I will put a adiabatic wall. Then what happens, this piston and cylinder arrangement becomes completely insulated, or adiabatic wall. But keep on do compression from 4 to 1. What happens, you are compressing, but there is no provision of heat transfer, there is no heat transfer at all, but still you are compressing. That process we can call 4 to 1, we can call compression process, but there is no heat transfer. That process we can call adiabatic compression. So 4 to 1 is adiabatic compression. So this is how does Sadi Carnot explain his engine. This is about Carnot engine working principle. Okay, now you can see one more diagram. Okay, what actually is done, he considered a heat source, that highest temperature it is having, that is represented as TH. Heat sink, it is having a temperature, lowest temperature, that is TL. When he is going to contact heat source to the piston with the help of insulating cap, he will remove that insulating cap. Then directly the heat source is going to connect to the piston. Hence the piston, what happens now, it will start to move from point 1 to point 2. You can see here now point 2. When it is moving point 1 to 2, that means what, the heat source is connected with piston and cylinder arrangement. Hence constant heat supplied takes place at a constant temperature. That process we can call it as a isothermal expansion. From point 1 to 2, what you done, you supplied heat at a constant temperature, that we can call it as a isothermal expansion. Why it is so, piston is getting expanded, that we can call it as a isothermal expansion process. Then what he will do, he will remove this heat source and he will put an insulating cap. Still it is the piston and cylinder, still it is having a heat source inside it. It will move from point 2 to 3. So that we can call from 2 to 3. From point 2 to 3 we can call it as a adiabatic expansion. Expansion is taking place, but that is adiabatic. Why so? Because there is no heat transfer at all. But during point 1 to 2, he supplies certain amount of heat, that is represented as a Q1. Okay, fine. Now again, this is what expansion. Now from 1 to 2, 2 to 3 expansion. One is isothermal expansion, another one is adiabatic expansion. Fine. Now reverse. The piston will start to move from 3 to next 3 to 4. You can see now 3 to 4. I will mark it here now. Assume that initially the piston is at particular point 3. You will start to do compression. Then piston is moving from 3 to 4. Whatever heat is there, right, it is going to transfer from system to the system to the surrounding. How it is, that you can see now. We will remove the insulating cap. We are going to attach heat sink to the piston and you are compressing. You are attach the heat sink to the cylinder and you are compressing from 3 to 4. Hence heat is generated. That heat is rejected from cylinder to the surrounding at constant temperature. That constant temperature you can call it as a T2 or TL. That heat rejected is represented as a Q2. Okay, from 3 to 4. Once it reaches 4, immediately what I will do, I will remove this heat sink from the cylinder. I am going to put an insulating cap. When we are going to put an insulating cap, complete piston cylinder arrangement is going to become adiabatic wall. Hence there is no heat transfer at all, but still you are going to compress from 4 to 1. That process we can call it as a adiabatic compression. So 3 to 4 is a isothermal compression. Then 4 to 1 is adiabatic compression. So 3 to 4, 4 to 1 is what? Compression process, whereas 1 to 3 is expansion process. To expansion process to adiabatic process we can see here now. So at 1 to 2, what you have done, you can see the same thing, you can see it in a TH diagram. Temperature, sorry, TS diagram, temperature versus entropy. 1 to 2, what we are doing, we are going to supply 1 to 2, we are going to supply certain amount of heat. That heat is represented as a Q1. Then temperature at point T1, point 1 and point 2 remain same, hence T1 is equal to T2, that is a highest temperature, hence we are going to show it as a TH, highest temperature. Okay, now 3 to 4 you can see here, dear students, the heat is getting rejected. That heat rejection is represented as Q2, that heat rejection is represented as Q2 at a point 3 to 4. So whereas this 3 to 4, temperature at point 4, temperature at point 3 are less compared to temperature at T2 and T1, hence T3 equal to T4, that is equal to TL, lowest temperature. This is how the Carnot engine work actually. So with help of this Carnot engine working principle, what we can do, we can calculate the work done. How to calculate the work done, we know. So what is work actually? So work done we can calculate it with help of heat supplied to the heat rejected. That means what? Q1 is heat supplied, Q2 is heat rejection. So Q1 minus Q2, we are going to get how much amount of work is done by the engine. So with the help of this heat supplied and heat rejected, we can calculate efficiency also. We know that efficiency, general efficiency is what? Output divided by input. Okay, what is output from the engine? What work done, right? What is input we are giving? Heat supplied. Heat supplied is represented as what? Q1. So therefore efficiency, how I can write now? What is W here now? W is what? Q1 minus Q2. So Q1 minus Q2 divided by Q1. So therefore that, like, how I can write now? So therefore 1 minus Q2 divided by Q1. This is what? Efficiency. With the help of this heat supplied and heat rejected, we can calculate work done as well as efficiency. Okay, and if I have data, other data efficiency, if I have Q2 or Q1, with this data I can calculate heat supplied or heat rejected also. Okay, this is what, how to calculate the efficiency parameters of a Carnot engine. Okay, fine. So now isothermal expansion, as I told, as in during isothermal expansion, what actually we are doing, we are going to supply the heat actually. That means what? Heat is added. Then which law that follows? Because we are using ideal gas in the cylinder, so it follows ideal gas law. Then adiabatic expansion. In adiabatic expansion, what happens? Temperature volume relations. Okay, the temperature, as the temperature increases, so as the temperature varies, volume is going to vary. Similarly, isothermal compression. What actually isothermal compression happening here now? At 3 to 4, heat is getting rejected. Hence, we can call it here heat is rejected. Again, we are using ideal gas, that follows ideal gas law. Then adiabatic compression. Again, here what happens? As temperature varies, volume also going to vary. This is about Carnot engine working principle, dear students. So thank you, dear students. Here I request you, please do subscribe my channel to get more and more videos related to all engineering thermodynamic subjects. Not only engineering thermodynamic subjects, you can get you can get PUC Physics 1 and Physics 2. In future, I am going to prepare some competitive exam question paper also I am going to solve. That to government exam, railway exam, boiler engineer exams. Okay, like that KPS exams. Lot of, where I am having a series of works to do future. So for that, I require your support. So please do subscribe, like and comment on my channel. Thank you.